Okay, and last class we started talking about the basically the normal distribution. We started talking about statistical distributions, and that's what I'd like to continue on today. Let me just see if I can adjust my screen internally, and if I can, this would be good. Maybe not. Okay. Okay, so let's start. Last time we were talking about statistical distributions. We talked about normal distributions. We talked about the interesting properties of normal distributions that that basically, since they are by definition defined by the mean and the standard deviation, we know exactly how much of the mass of a normal distribution lies a certain number of standard deviations away. And this tells us, you know, this is a good thing about it. Data that's normally distributed. Data is not usually really exactly normally distributed, although it's a good approximation. And you know, but be aware of things like mixtures of populations. Any questions about normal distribution or anything like that? If you've got a camera, I'd like you to turn it on if possible, just to see if people are alive out there. But I'd like to now continue on with today I'd like to talk about two other classes of statistical distributions that are kind of important, okay, and to be aware of. The first is a distribution that is good at modeling lifespans of things. So if you think about what your lifespan is going to be, every day you are going to wake up in the morning and you're going to do one of two things. You're either going to keep breathing or you're going to stop breathing. And let's say that on a particular day, everybody, let's say, had a 1 in, you know, 20,000 chance that today is the day you're gonna stop breathing. How long would be your expected lifespan? Okay, or what would be the probability of living exactly a certain number of days? My claim would be that if the probability of surviving on a day is P, okay, let me write that down. Actually, hold on. Boom. If the probability of surviving on a given day is P, the probability of dying on a particular day is 1 minus P. What is the probability that you will live to be exactly n days long? It means that n minus 1 days in a row, you woke up and breathed. So with the probability would be that for the first n minus 1 days, you were breathing, and that was probability of P every day. So it's P to the n minus 1 times the probability that on the nth day you stopped breathing. Okay, so this gives you a probability of how living exactly n days, and that gives you a lifespan distribution. Okay, and a lot of problems. We're kind of interested in a lifespan distribution, a distribution between two rare events. Okay, we talked at one point about light bulbs, and suppose I knew that a light bulb lasted 1,000 hours on average. What did I know about the distribution of how long light bulbs should last? You know, and we said, well, it could be that, is it that there's kind of a bell-shaped thing? Is it that they all die on exactly the 1,001st hour? Well, I think a distribution like this probably kind of captures what happens in a light bulb. When I turn on light bulbs usually, if they're going to burn out when I actually try to turn it on. Okay, and so you can kind of imagine every time you're pulling the light bulb cord, nature, there is a certain probability that it's going to burn out or not burn out. The lifespan of a bulb is going to be how many events did it not burn out, followed by the probability it burnt out right after that. And if we had a certain expected amount of time we leave a light bulb on, this probability P kind of falls out naturally if we know how long light bulbs go on, what you call it, on average, how long you leave them on, and you know that the bulb is supposed to last 1,000 hours on average. So lifespan distributions are captured. Any questions about that? Lifespan distributions are captured by the Poisson distribution. And this is one that is kind of an interesting, again, what's the Poisson distribution supposed to do? It is supposed to measure kind of the frequency of intervals or the length of intervals between rare events, okay? And the probability, okay, of, you know, an interval, a lifespan, a gap between two events, okay, is of length x is going to be the expected time. You know, the mu is the expected value. X is, you know, what we want to know about, divided by x factorial times e to the minus mu. So if I take a look at this, this is an exponential, okay? N factorial, okay, is an exponential thing. It can be written as e to the something, okay? This is an e to the minus something, okay? This is a mu to the something. Anyway, this is what the Poisson distribution is. The interesting thing about the Poisson distribution is that it has exactly one parameter to it. The only parameter we have for it is mu, the expected, okay, okay, the only parameter we have for our distribution is mu, the expected lifespan. But if you know that your the lifespans are governed by a Poisson distribution, then this enables you to figure out what's the probability of any lifespan, okay, just given mu, okay? Any questions about that? Again, it is kind of interesting to think about. The, you know, when I was giving the light bulb distribution, I said, or the how live to a certain number of days, okay? What you call it? All that you were given was a probability P. What's the probability of surviving to the next day, okay? It's often hard to figure out what is the probability that someone's going to survive to the next day, but it's easy to tabulate what the expected lifespan is, okay? So what's good about the Poisson interval is that, what you call it, it's parameterized by something easy to calculate, the mean, easy to observe and get statistics on. But of course, since we know how to compute what's the probability of living to a certain age given P, the interesting thing is just that a given mu defines essentially what that underlying P is. And that's why the just knowing the mean is enough to plot the history of the standard for the Poisson distribution. Any questions about that? Out of curiosity, how good a model of this do you think this is about lifespans? If you want to try to think about predicting lifespans, does it make sense that lifespans are Poisson distributed based, trouble. Let's get back there. Does it make sense to you that the lifespans are Poisson distributed according to this argument? Yes or no? Anybody like it? Anybody not like it?
The probability of surviving is not always P, it depends on the age and other factors.
I couldn't quite hear you. Try that again.
I said that the probability of P should not be constant over a lifespan. It
Okay,
should
so
vary.
now this is a great idea if the probability of dying on a particular day is constant over the entire lifespan. Okay, do we believe that that's true in what you call it for people? And we sort of think that in general, it probably isn't. Okay, you kind of think that there are, you know, like, you know, a 3-year-old baby shouldn't have any risks of cancer. That's something that happens when you get older. Okay, a 3-year-old baby shouldn't be getting into auto accidents, things like this. So in fact, I guess what you would be saying is this kind of a model probably makes sense, but you don't like the assumption that the probability is constant. Okay, and that is a fair thing. You know, so there is actually you know, a lot of work done on what is the actual right modeling for human lifespans. And one thing that's surprising actually is, yes, P is not a constant, but it's surprisingly constant when you get up to older ages. So like, you might think that if you're 100 years old, you have a much better chance. If you have somebody who's 100 years old and someone who's 106 years old, what's the likelihood of them dying the next day? Okay, it's surprisingly constant, actually. Okay, but not over the whole lifespan distribution. Okay, but this should make it sense that as a first-person principle model, this is kind of a reasonable idea. And if I have to guess, I would say human lifespans are Poisson distributed. When I actually try to fit it, it's not quite, and I have to go to a more complicated distribution. Any questions about that? What is another example of a distribution where I think that there is a event? Okay, life progresses as a sequence of events. Okay, and that has to do with how many children are in a family. Okay, you could imagine a model where when a family gets together, they flip a coin, you know, mommy and dad, you know, a potential mommy and potential daddy get together. They flip a coin and decide whether to have a kid, okay? Or shut down the factory entirely, okay? And then they have another kid and they decide, am I gonna have a kid, more kids, or am I shutting the factory down entirely, okay? If we had a model like this, okay, then, you know, what you would call it, then family sizes would be, how many times did they decide to have kids before deciding not to have a kid? Okay, if you believe that, then if you know the average number of kids in a family, you should be able to predict what the number of what percentage of families have three kids, 5 kids, 7 kids. Okay, you know, historically, people used to say, it's not, I think, quite true anymore, that the average US family had 2.2 kids. If you have 2.2 kids, and that's all you know, and you assume it's a Poisson distribution, you can now come up with a guess as to what fraction of families should have a certain number of children, okay, of a certain size. And I found it actually very hard when to actually find data on this. But again, when you look at the this side of the distribution, what's the number of families with 8 kids, 9 kids, 6 kids? It actually fits it surprisingly well. Okay, so the power of the Poisson distribution is just given an easily observed thing. If you think of it in terms of a Poisson distribution, you can get a probability distribution from just the mean. Okay, and often it's a perfectly reasonable assumption if you see it the right way. Any questions about that? Any questions about Poisson distributions and why they are good things? Okay, again, if all you can do is measure a mean, this has the property that you can get a probability distribution about it. Of course, you've got to make sure that the probability distribution fits what you want it to, and that there's a the distribution is defined because of the reason of this. Any questions? Okay, good.
I had a question.
Yes.
For the Gaussian distribution, for Poisson distribution, we have these equations. And is there any intuition behind these equations, or is that just solving a really complicated problem with integration and we come up
Okay.
with this
You mean
formula?
where did Gauss? You mean is this what you're talking about? You want to know where
Yeah,
did Gauss come up with this?
yeah,
Okay. And the honest to God truth is, I am not, I have always taken this as a given. I believe Gauss did this as his doctoral work. Okay. So, so I don't, to a certain extent, so I don't know exactly, so let's say the short answer is I can't give you a derivation or intuition of exactly why this constant is what it should be or something like that. Okay. But presumably if you read a book on statistics, it'll kind of make sense. Okay.
okay, okay,
But again, the important point as far as I'm concerned with it, I know the shape of what the normal distribution looks like. I know what its properties are. I like the fact that it's parameterized by two things, okay, that I can generally pretty easily observe, okay, and that distribution fits a bunch of things that, generally fits a lot of things that I see in practice. Any questions? Okay. Any questions on the Poisson distribution? Okay. The last distribution I want us to be aware of here, which is important, is the power law distribution. Again, we've talked about it a little bit. We'll probably see it again a couple of times, okay? A power law distribution is a distribution where the probability of getting a value of x is x raised to the minus a, okay, times some constant, okay? Let's think what that means. As x gets big, what happens to the probability here? Okay, if we think about something like that, let's say that a is, in a typical case, is 1. So suppose we have a probability of x is equal to some constant times x to the minus 1. What happens as x gets big? What happens to p of x? Anybody? Okay, it gets small. Okay, it's something like this. This is now 1c over x. As x gets big, the probability of seeing something that big gets small. So this is something that reduces. If x is bigger than minus 1, let's say it was minus 2, okay, it gets small very, very even faster. Okay. What is interesting about this thing? So in a power law distribution, it's not a world where there is, if you look at what is if this is x, if you look at what the probability of x is, it looks something like that. It goes down rapidly. There is not a center, okay? Instead, what happens is, it's funny, it goes down rapidly, but it doesn't go down exponentially rapidly, okay? It means that even for very large values of x, okay, you end up having a non-trivial probability of that possibility existing. If we think about a Gaussian distribution, one thing that we saw, again, there was some looking at what that formula is, okay? The truth is that the probability that you're going to get something that's far from the mean goes down exponentially. Here, it's going down linearly or quadratically. The net result is that you can have a non-trivial probability of getting very, very large values, even though you have a high probability of getting small values. That's one of the issues in a polynomial, in a, in a power law distribution. And power laws distributions come up whenever you have kind of a, people talk about as being like an 80 or 20 rule. If 20% of the people get 80% of the money, okay, then the probability of, if that's true for any group of people at any point on the scale, if 20% of the billionaires get 80% of all the money owned by billionaires, okay, you end up getting some people who are unbelievably richer than other people, okay? When you have a rich gets richer argument, okay, then you end up getting a power law distribution. Any questions? And there's a lot of things in the world which naturally are defined by power law distributions. What you call it? And as an example of it, let's look at city population. Okay, I took a data set where I took a list of all the cities in the United States. And the average thing big enough to be called a city in the United States had a population of 165,000. There was something like, there were a few hundred cities in the United States. The average population was 165,000. If you took the standard deviation of the population, okay, which happened to be pretty big compared to the mean, if we assume that things were normally distributed, if we only have a few hundred cities, okay, the probability of getting any city that is more than like 3 standard deviations away is going to be almost nothing. 2 standard deviations from from the mean worked out to be Indianapolis. But Manhattan, New York City, has 8 million people. Why is it that New York, does everybody see that, again, if you're believing my issues on the number of cities, if you tried to assume it was normally distributed given this mean and this standard deviation, it should be clear that New York City is an incredible outlier, okay? It could not happen if city populations were normally distributed. Why is it that New York City is so big? Can anyone tell me why the population of New York City is so big?
I think it kind of turns into another rich get richer situation where once you already have a large city, it has large opportunities, lots of resources, which in turn attracts even more people, and it continues to snowball.
Exactly right. New York City's population is so big is because it is so big. Okay, people go to New York City because it is big. Okay, they want to experience all the opportunities of the big city. Okay, and so it is, in some sense, the bigger the city is, the more attractive it is to other people, okay? And it keeps sucking things up. That is exactly what a power law is, okay? Any questions about that? Okay, so this is kind of, the rich gets richer is the mechanism that causes power law distributions. And again, let's look at what happens. This is actually my plot of the city data, okay? The x-axis is, if you look at it, the x-axis is the rank of the city. So from the biggest city to the smallest city. As I recall, they defined a city as being a city if it hit 100,000 people or something like that. What do we look at when we get a plot where the x-axis is the rank of the city and the y-axis is the, the population? What do you see here? Okay. I can tell you one thing you don't see here. You don't see Manhattan. Where is Manhattan? Where is New York City? Okay. This spot goes up to 600,000. Where is Manhattan? This is 1 million. This is 2 million. This is 3 million. Does everybody see that New York City is way off this plot? Okay. In fact, you end up having a curve that kind of goes like that. And, you can't see a meaningful plot of a power law variable if you have them, you know, if you show the biggest ones. I deleted like the 20 biggest cities here because you couldn't possibly show them on a map. Now, what happens on the other hand if you plot it on a log scale, a log-log scale? If you take this situation, and this is a log scale, notice that the distance from 1 to 10 is equal to the distance from 10 to 100. That's what it means to be on a log scale. Okay? Now, when I plot the log of the population, okay, against the log of the, the log of the population against the log of the rank, now you see that over a long period, it falls on a straight line, okay? That straight line, the slope of that straight line, define that minus x, remember I said it was something like x to the minus a? A is kind of the slope of this line, okay? And when you plot a, the way to think about what a power law is, when you plot the variables on a log-log plot, you should see a straight line. And so typically what you end up seeing is there's a large chunk here that is, straight. There are some other points where it thins out that are probably typically on it, or maybe there was some other little garbage at the beginning and some other little garbage at the end. But usually you will see a straight line on a log-log plot where it is interesting. Any questions about that? Okay, so whenever you see a figure where where your biggest value is so thoroughly dominated, plot it on a log-log plot and see if you got a straight line. Okay, again, wealth is a power law thing. The more wealth you have, the more wealth you get disproportionately. Okay, if wealth was a power law, okay, if you had a world like something like this, where every time you double the wealth, let's say you have 1/5 as many people as had it before. If so, what would our situation be? We would have a world where there were only, at the time I made it, 625 people who had 5 billion. In this case, twice as much, I had 1/5 as many. Twice as much, I had 1/5 as many. Twice as much money, I have 1/5 as many. Twice as much money, I have 1/5 as many. That's what happens with a power law, okay? When you multiply the value of your variable here, money, you divide the number of people with it, or the probability of having that much money, by another constant. Okay, the ratio of these constants is that power law constant that we had. Any questions? Okay. Why is it that wealth observes a power law? Okay. It's not just that, that I am investing in something and I earn the same interest rate as Bill Gates does. It's that the money that the wealthier people get better opportunities to invest, okay, and their money can kind of earn bigger returns than other people, okay. If you have a rich gets richer world, you have a power law. Any questions? So what is the, again, as I said, what is the distribution defined by? It's defined by the equation like this, where the probability, if you have a random variable x, the probability that the wealth or the population or something like that was exactly x is going to be some constant times x to the minus a. This constant c is not that important, okay? The only reason we worry about the c is in order for a probability distribution to be a probability distribution, it had better be the case that when you integrate it as x goes from 0 to infinity, okay, the sum of the probabilities should be 1. Okay, that constant only exists so that the probability is going to be 1. Okay, but think what's going to happen here. If I take, if I take my value of x and I double it, what's going to happen to the probability? The probability for x would have been c x to the minus a. If I double it, what do I get? I get c times 2x to the minus a. This is going to be c times 2 to the minus a times x to the minus a. Does everybody see if I look at the ratio of these things? Okay, the ratio, everything's going to, this is going to cancel. And it basically says that as I doubled x, my probability dropped by 2 to the minus a. Okay? And so what that means is that's kind of the same notion that in a power law, you double something, the probability drops by a constant fraction. Okay? And it will keep doing that over the whole range of the distribution. The probability as you keep doubling the wealth gets smaller and smaller and smaller, but it doesn't go to 0. Any questions?
Is A typically a fraction?
What?
Is A typically a fraction?
Is A typically a fraction? I would say A is typically a real number, which is basically a fraction. So you want to say, is A typically less than 0? I mean, less than 1. Is that what you're trying to say?
I'm asking if, like, in practice, when you're trying to fit data, whether you usually get an integer for A or whether A is...
No, you usually do not. There's no reason why you need to get an integer for A. Okay? So typically when you fit when you fit one of these things, you're not going to get an integer. Typically. Okay? Although the most famous power law distribution, A is an integer. But in general, A does not have to be an integer. Okay? What kind of things are power law distributed? Okay, well, probably the most important, the one that you're probably most familiar with is the idea that, the number of, the number of, let's say internet sites or websites have X things pointing to it. The more you have X increase, okay? If you say how many websites have one thing linking to it, how many have 2, 3, a billion, 10 billion, okay? If it's a power law, it would be an argument that as we double the number of links, the number of sites that received that links went down by a constant fraction, okay? And, this is what is observed in, this is what is observed on websites, okay? And the only reason that would happen is if, I guess it's actually this one. It doesn't really make much difference. This is probably the box I'm talking about. Why is it that we have a rich gets richer, that more popular sites are kind of more frequent than you would expect with a normal distribution? Okay. Why is it that you would expect that if a website has become a little more popular, it's likely to continue to get, if you have 2 websites, one's popular now, one's less popular. Why do we think the more popular one is more likely to keep growing and get more and more links? Okay. Okay. Maybe, there's typically if you are a more popular site, you're more likely to be seen in Google. Once you're seen in Google as the top one, more people will link to you. Okay. Generally speaking, the more people that use a website, the better the website is, and the more people it attracts, and you end up getting a rich gets richer phenomena. Any questions? What's another example of a rich get richer phenomena? If you look at what is the number of sales of the most popular book, again, I like to write books. I like to look at Amazon and see where I am ranked on Amazon has a, where are you ranked on our bestsellers list, okay? If I know that my book is the 25,000th most popular book on Amazon, what does it mean for sales? How does the 25,000th book compare to its number of sales to the 50,000th ranked book? I am twice as big a rank. I probably have a constant fraction more sales. Okay, maybe I get twice as many sales. Okay, if so, I can guess based on how many sales I have, what the number of sales of the best-selling book is. Okay, if it observes a power law and I know what that A is. And is there a rich gets richer mechanism in in book sales? The more popular a book is, the more likely it is someone famous will read about it and talk about it on their talk show, right? The more likely that that publisher is going to spend money and advertise it, right? So the more popular, more likely you're going to hear from somebody who said, oh, Skinner's book, that's great, okay? Does everybody see that there is a rich gets richer phenomena? And that's usually what drives these power laws. And again, a typical power law distribution on a log-log plot, you end up getting a large linear region. Sometimes there's weird things at one end of the tail or the other end of the tail. But if you have this, it becomes a power law. Any questions about power laws?
Does it relate to the network effect? Like we have more connection, you have more strong. Yeah,
power law is basically the consequence of the network effect. The network effect says something that Facebook is more useful the more people that are on it. Okay? And therefore, I'm more likely to join Facebook because there's a lot of people that are already using it. That is why you end up getting, that's basically the same mechanism as to why there tends to be one platform, okay, is the same thing that tends to be drive these kind of power laws. It's a rich gets richer phenomena. Any questions?
Most power laws are log-log, or it depends on the outlier.
Say that again?
I mean, most power laws distribution are log-log distribution, or it depends.
Yeah, so by definition, if you have a power law distribution, by definition, if it observes that power law distribution, it will show up as a straight line on a log-log plot. And the slope is going to be what defines that parameter alpha. Okay, any questions? And again, there are a variety of natural things. Wars. For each war, how many wars do you have that kill certain numbers of people? This is a graph of an interesting thing. X here is the number of people killed in your war. Y is the, as we go from the, how many wars, what fraction of wars are there that killed 10 people, 100 people, 1,000 people? When you plot violence like that, people tend to see a power law. And one consequence, that means that wars that kill huge numbers of people are rare. But it also means that there is no upper bound, okay? Why haven't we seen a war that killed a billion people yet? If wars are power law distributed, it's because we haven't waited long enough, okay? And that there is a low probability of a war breaking out that is going to kill more people than ever we have ever seen before, okay? Any questions about that?
Professor?
Yeah.
But for popular sites or people with fame, like they don't stay at the top of the rank always. So for this distribution, do we need to define a time period as well?
So you're telling me that there are certain phenomena of time periods. Well, let's look at something like book sales. Book sales, okay, what does this distribution? The X was, okay, in a power law distribution, we want to know what is the you know, in sometimes when we look at the Zipf law or something like that, you want to know what's the frequency, okay, let's say the number of sales of the most popular book, the second most popular book through the nth most popular book. The argument is that this distribution is going to stay the same. Although week to week, what is the most popular book or the most is going to change, okay? So there is a temporal component to it, but it's still the claim is that, that if you look at a power law distribution of how many sales were there this week, the most popular book is going to sell 10 times what the 10th most popular book is, okay? And that's kind of what the power law distribution is. Any questions? And again, I used, for book sales, I was kind of assuming something called a Zipfian distribution, okay? Zipf's law, okay, is a law that says that, which was observed first about use in language. It said, what is the frequency of the kth most popular word in a language? The claim is that it should occur 1/8 as often as the most popular word. Okay? So let's say the most popular word is the. What would we expect the second most popular word to be? Or how often would we expect it to occur? We would expect it to occur half as much as the does. Okay, and again, this is a log plot, if I am correct. Okay, I think it said logged, right? But on this world, what we end up getting is, in a Zipfian distribution, you say that the popularity of the kth most popular thing is 1/8 of that of the most popular, okay? And it fits the use of words in languages amazingly well. Okay, if you plot the frequency of the ith most popular word in English, okay, you end up getting a power law distribution, and Zipf's law is what you get when you get a power law where A is 1, okay? And that argues that when you double the rank, going from the X most popular word to the 2X most popular word, the frequency drops by 1. By a half. Okay? Any question? Any questions about how Zipf's law works? Okay, and it works this way in all kinds of other languages. Why do we think, is there a rich gets richer phenomena in language? Would we think that more popular words would tend to be, you know, used more? Well, it's probably true that if you're learning, when you guys were learning, many of you didn't speak English as your first language, okay? Did you learn the more popular words before you learned the less popular words?
Yes.
Almost certainly, right? And that may be one of the things that kind of drives this thing, okay? That the more popular words are the ones that people use a lot, okay? They know what it means. Once you know what a word means, you're more likely to use it. Once you use it, you get used, you know, you use it a lot, okay? Any questions about that? Okay, so what are the bottom line? What are the properties of power laws? One is the mean of a power law isn't really as valuable a statistic as you would think, okay? Bill Gates by himself, okay, adds about $250 to the mean wealth in the United States. Do you feel any richer because Bill Gates is in the country? Okay, and the answer is presumably not. Okay, what is a better statistic for measuring the behavior of capturing a power law variable? Typically the median. Okay, Bill Gates contributes almost nothing to the median. The median salary would be the wealth would be the one where there are half as many people below it, half of the people above it. Okay. It's also the case that any questions about that? I think that should be obvious. The other thing that's true is that the standard deviation of a power law doesn't really make sense. Think back to our city example here. The mean was the, the average population. The standard deviation of populations of cities was very large relative to the mean. If the standard deviation is large relative to the mean, that tells me that, you know, the distribution is all over there. Think about height. The average height of a person is about 5.5 feet, 6 feet. The standard deviation is probably about 6 inches. We're used to worlds where the standard deviation should be a lot smaller than the mean. That's not true in power laws because it's not centered around something. Okay. What is the other property of a power law? Because it has this property that it's always the case that when you double the number, you want to know what's the probability of the 2x most popular item is always, let's say, twice that of the x most popular item. The power law is what we say scale invariant, meaning when you zoom it in, it looks just like the entire plot. That's kind of a weird thing. If you looked at the, here we've got the, the distribution of frequency of words, okay, as a function of rank. If I zoom in on any given point and I plot the words, what am I going to see? I'm going to see a curve that looks essentially the same thing. It's going to have the same shape. The property of the power law distribution is it kind of has the same shape over any place where you look. That's what they mean when they say that it's scale invariant. Any questions?
On the slide with Zipf's law.
What? Oh, sorry, I can't hear you. Speak a little closer.
On the slide with Zipf's law.
On the slide, what?
On the last slide. The rule that the second most popular word, which seems to be of doesn't look like it is half the popularity of the.
Okay, well, notice that this is not a log-log plot, first of all. This is logged, right? Does this say logged? I think I see the word logged. Okay, and this is not logged. Okay, so the reason you're trying to say this is not half of that thing is because this is in log space. Okay, but generally speaking, it's an argument that the frequency of the word of the second if it was observing a power law distribution, the second word should have half the frequency of the first word. Okay, and generally speaking, it fits, you know, it fits Zipf's law quite well, okay? Well, what it says on this date plot, I'm not even gonna look at too closely, okay? But this is actually an interesting thing to plot if you've never done that before, okay? So take a big enough corpus, take a look at the frequency of words, and I think you will see that it observes Zipf's law actually surprisingly well. Any questions?
Yeah, that answers it.
Okay, any other questions about power laws? Okay, good. If that's so, I would like to now start to talk about another aspect. So we now should know basic distributions, okay, that come up a lot. I'd like to talk about one other aspect of statistics that is very, very important, which is that of how do you measure the significance, the statistical significance of results. So when you talk to statisticians, again, I am someone who spends a lot of time actually doing interdisciplinary things. I spend a lot of time talking to people in biology and in the social sciences, and I'm now talking to neurosciences. I usually am able to communicate with these people pretty well. I often have a hard time talking to statisticians. And one of the reasons is kind of a data scientist and computer scientists and statisticians are relatively close. And when you have two communities talking about the same thing, sometimes they see things in different ways. Now, in general, a data scientist, a computer scientist, a data miner typically is looking at a data set and very concerned with identifying what things are interesting. Now, statisticians, as a rule, if you say what drives them, they are very concerned with making sure that anything they observe is provably significant, okay? That it didn't happen by chance, okay? Now, I have a hard time talking with statisticians, but they are often right about things, okay? And what I would like to talk about here is questions of how would you actually argue that something that you observe in the data is interesting, okay? There was a question on the previous talk about power laws, and I was telling I was glibly saying that the frequency of the second most popular word should be half that of the most popular word in English, and they were doubting me. Well, they were thinking that if they did, then that's good. It's good to be skeptical. You should look at data, and you could imagine now trying to argue whether I'm right or whether I'm not right. Okay, you would have to look at a bunch of data sets and come up with an argument of, have you seen enough data evidence that something that in fact the second most frequent word basically occurs half as often as the most frequent or not, okay? Trying to argue rigorously that you have proven that is what significance is about. So significance is about when is an observation meaningful, okay? When we look at data sets and we see patterns and we draw a picture, we're often able to tell whether we think we see things in it, okay? But often there are, it's hard to know unless you do a significance test whether an anecdotal evidence is meaningful or not, okay? And that's one of the reasons why we would like to have a more rigorous way to tell whether our observations are meaningful. This issue is, I think, most obvious these days because we're all living in a world where you have companies racing to try to come up with a vaccine for COVID, okay? They're trying to come up with drugs that will try to treat it better than some other drug, okay? The world where statisticians really earn their money is in medical analysis of drug testing. Often when you have a drug trial, you don't have that much data you can look at. You have very small amounts of data, okay? You may very well have a situation where you have, let's say, you want to run a study of whether some drug is going to save the lives of COVID people. How do you do this test? You've got to convince patients to take your drug instead of the thing that the doctors normally use to try to save lives. So typically they give, when you sign up for a drug test, you can either take, they will say, we're going to give you either drug A or drug B, and we're not going to tell you which one you're taking, okay? Suppose we had drug A and we gave it to 34 patients and 19 of them got better. Suppose we took drug B and we gave it to 21 patients and 14 got better. Is drug B better than drug A? Okay. Does everybody see that this could have very well happened by chance? We had this issue when we were talking about baseball batters, even if they were 30% hitters. Sometimes they had good seasons, sometimes they had bad seasons. And it was purely about whether the drug got lucky or not lucky. Trying to do an analysis to say, is drug B really better than drug A? Okay, and by how much? This is a statistical test, and we would like to know that, with a certain level of confidence, we believe that drug B is better than drug A. If so, we will license drug B, and the company can sell it and make money. And if not, we're not going to let them do it. Any questions about where significance plays a role here? It's about whether we see an observation and whether we believe it's right. Any questions? Okay, bing. Now, one place where significance testing is actually kind of important to being an honest scientist has to do with evaluating whether your machine learning model is better than some baseline or better than some other machine learning model. Typically, what people will do is they will try to write a paper to find a machine learning classifier to do good at task X. They will keep beating on their model and change it and do this kind of thing until it gets a higher score on average than than some other model. The question of whether they got lucky or whether there's really a difference between the two models, that is the kind of thing that you would like to use a significance test to try to tell you. Too often people publish things where they say, the other group got this, I got this little thing better than them, my model is better, okay? And significance testing will be the kind of thing you would do to tell me, convince me, what is the likelihood that this happened for real, or what is the likelihood you just got lucky? Any questions? Okay. So what is an example of a statistical test for significance? Okay. Probably the most famous statistical test is something called the t-test. Okay. It says you've got two different samples of a population. You'd like to be able to know whether the two populations are really different or if the samples are being drawn from the same distribution. Okay. Let's say, for example, we had some treatment for lifespan. Let's say lifespan is good. You have a drug for cancer people, okay? And you have people in one cohort who took your drug, okay? You gave it to 20 of these people and they lived out their lives. Some died younger, some died older. You had another group of, let's say, 20 people who you did give your drug to, okay? Did the cohort is the cohort that got this drug different than the cohort of that did not get the drug? Okay, did their lifespan show a significant difference? Okay, so typically we are interested in comparing whether the mean, let's say, of lifespan of the people who took the drug really is bigger than the people who didn't take the drug. Okay, any questions? So let's think about what a t-test should do, okay? Suppose, let's take a world where we don't necessarily think there's going to be a difference, okay? Suppose I want to find out whether men are smarter than women, okay? Suppose I took 20 men from the class and got their IQs and computed the average. And I took 20 women from the class and I took their IQs and I computed the average. Do we think that the IQs of the men and the women are going to be the same on average? Any opinions here? What should happen if I took the IQs of men and women? Okay, sample of 20 of them. What do we think about the average? Is the average going to be the same?
Since the sample sizes are so small, probably not. The sample mean won't be the population mean, so you'll probably see some variation between the two groups.
Okay, so one question is the sample, if the sample is small, okay, probably not. So if I had, let's say, like one man and one woman, are they likely to have the same IQ? Okay, well, IQs range over, probably the people in this class have IQs that range over a 20 or 30 point scale. It wouldn't surprise me from max to min. Odds of them being the same, low. If I had 20 of them, is the likelihood that the average is going to be exactly the same? Low, okay? The real question is, so there's going to be a difference if I take a sample of 20. The question now, so either the men are going to be smarter on average or the women are going to be smarter on average. The real question is this due to sample bias or is there a meaningful difference? There's going to be a difference almost certainly, but the question of whether it means something is what we would like a t-test to do. So how can we tell whether two distributions are the same thing? One of these might be male IQs, one of them might be female IQs, or male height, or male female, or people who took lifespans of people who took drug A and lifespans of people who took drug B. How easily, if we had a distribution like that, could we tell them apart? My claim is that the further the means of the distributions are, the easier it is to tell them apart. It's easy to tell that men and women have different average heights. Why is that? Well, it's a non-trivial difference. I'm going to guess it's something like 5 or 6 inches on average or something like that. Okay? Now, for something like IQ, if there is a difference, and again, I presume there's no difference, so let me make that clear. Okay? But if there was a difference, it would have to be a pretty subtle thing. Okay? It's easier to tell distributions, okay, apart if the means are different. Okay? The range where they overlap becomes less if the distributions have means that are far apart rather than when they're close. Does everybody agree with that? It also becomes easier to tell whether two distributions are different depending upon what the variance of it is. Okay? If you have two distributions, okay, where the variance is extremely small, okay, it's easier to tell those two populations about. Okay? Let's say, we wanted to tell whether or not 60-year-old people were older than 20-year-old people. Okay? How would we know? Suppose I plot the age. Well, 60-year-old people, the average age of them is 60. But what's more interesting, every single one of them would have an age of 60. There would be very little difference. There's no variance in that distribution. Would we be able to tell 60-year-olds from 59-year-olds? Well, if the two populations were such, we could tell because the variance in their age is very small. Okay? In a world where the variance is large, the distributions overlap by a lot. When the variance is small, there is less overlap of the distributions. So what is a t-test? What is the way that a t-test works? A t-test is going to take advantage of the fact that if we want to know how much do we believe that two distributions differ, we would like it to be the case that it's more likely they differ if the mean difference is large. It's more likely they differ if the standard deviation, the variance, is small. And it's more likely they differ if we have seen a lot of samples. Does everybody agree that if I have a lot more observations, I probably am more likely to believe a mean difference than if I just had one or two or a small number? So what is the t-test? The t-test works by taking the information on the mean, the standard deviation, and the number of samples, okay, and compute a statistic, which is called the t-statistic from that. In a particular flavor of the t-test, okay, what do? The t-statistic is if we have two populations, we say, what is the difference between the population means? That's the numerator. And we divide it by the square root of the square of the standard deviation observed from the first distribution. That's the variance. Divided by the number of samples from the first distribution, plus the variance in the second observed in the second distribution, divided by the number of samples. What's interesting about this statistic? As the difference in the means get larger, what happens to the value of the t-statistic?
Gets larger.
It gets larger. What happens as the number of as the standard deviation gets lower? Okay. Suppose we have we're having a number and we're dividing it by something. If we are dividing it by, if the standard deviations become small, let's say the standard deviations were 0, okay, then we are dividing it by 0. Dividing it by something small makes the number larger. Does everybody see that? So as you lower the standard deviations, the t-statistic gets bigger. Okay? And as you raise the sample sizes, as n gets larger, the variance over n is going to get smaller and smaller. If eventually it gets to 0, n gets large enough, if n became infinity, the contribution would be 0. Okay? As n gets larger, the t-statistic gets larger. Okay? So what is the t-test? The t-test computes this magic statistic and then looks things up in a table. Okay, associated with the statistic, with the t-distribution test is a table that says that if you have a, a t-statistic of this, okay, and you want to know whether your significance is, you want to know whether the likelihood of seeing this big a t-statistic, what's the probability of seeing this t-statistic, okay, is less than 1 out of 20 or less than 1 out of 100. Basically, you look that significance up in a table, okay, and that will tell you basically whether it's significant or not and what's the likelihood that that would have happened. Any questions about it? The basic mechanism by which a t-test works. Okay, we compute a statistic. There is then this magic table that tells us what the probabilities work. I find statistical tests like this kind of opaque, okay, because there is kind of this process of looking something up in a table, okay, but somehow where did the numbers of those tables come from? Where was it that these tests kind of were derived from? Okay, well, the kind of logic that goes on to it, okay, is using things like, we want to know what's the probability that if we drew samples, our observed samples came from a given mean and standard deviation. We can say, what's the probability that we lie very far outside of that? This should be bounded by various laws of sampling. Okay. We have Bayes' theorem. Okay. We are kind of going to be interested in what's the probability Okay, normally when we see data, it's easy to compute. What's the probability we see some data given a distribution? Okay, this can be converted to what's the probability we see we have a particular distribution given the data, and that's kind of what the these t-tests are saying. What's the probability the second distribution came from the same thing as the first distribution, given the first kind of data that we saw? Any questions about it? Bottom line, if you want to know whether two populations have a meaningful difference, a t-test is a good way to do it. Any questions? There is one other statistical test, classical statistical test, that I find very, very useful. And I find that, you know, I like and use, you know, I happen to use it more than a t-test, okay, just because it makes more sense to me. It's something called the Kolmogorov-Smirnov test. This is trying to tell if I've got two different samples drawn from two different distributions. I've got my men and their IQs, I've got my women and their IQs. What is the likelihood that they were drawn from the same distribution? That's kind of what we wanted to do. In a t-test, we made that decision based on the mean and the variance. In a Kolmogorov-Smirnov test, are often called the KS test, okay? What we do is we make that decision by looking at the cumulative distribution function of the samples, okay? So what do we know? Suppose in our world, all the values, okay, that we were sampling lie between -4 and 4, okay? If we did a cumulative distribution, okay, we would like to know, as a function of x, what are the number of samples that we have that are less than or equal to x? As x gets big enough, eventually all of the samples are less than x equals 4, let's say. Here, it turns out all the samples are less than x equals 4, okay? When x gets large enough, we will have seen all the samples, okay? When x was small enough, we would have seen none of the samples. So for each of our populations, we can compute a cumulative distribution of that, okay, and draw a picture of it. Maybe the reds were the men, maybe the blues were the women, okay? And when we look at these cumulative distributions, if we want to know whether the distributions are the same, the cumulative distribution should look the same, okay? If they look the same, there should not be any point on this spectrum where there is a big gap, no value of x, such that the number of things less than or equal to x, okay, on one is substantially less than the number of things on the other, okay, distribution. And when I'm saying number of things, I really mean the fraction of them. So you can use this for things with different numbers of elements, okay? But the claim here is that if you have a samples drawn from the same distribution, if you took a look at the, if you took a look at the cumulative distributions, we would expect them to be fairly close. How are we going to define fairly close? We're going to say that the maximum observed difference, okay, is small. What are we going to do? We're going to be saying here that the, sorry about this, this is bad, that the, that we're going to compute the maximum deviation, the value of x for that has the maximum difference between the two distributions. And we're going to ask whether the difference between those distributions is greater than or less than some constant C alpha, okay, times something that's proportional to the sum of the sizes of the two things divided by the product of the sizes of those things. Let's think what that, any questions? Let's think through what that, any questions? Yes.
How, I don't understand how this is like a measure of probability, but I guess you're answering that.
Okay, do you see why these are probabilities? These are observed frequency distributions. By dividing our counts by n, we get a cumulative probability, a cumulative distribution. Okay? Any questions? Okay? What is this saying here if we read this a little bit more closely? Let's say that n is the number of samples in each side is about the same. Okay? This here is going to be something like the square root of 2n over n squared. What is that going to be? That's going to be something like the square root of 2 over n. Okay? Which means that if we have n samples, we're kind of expecting that if these things are drawn from the same distribution, the biggest gap between the our observed thing and our the observed places should still be basically no more than a constant times 1 over the square root of n. Okay, 1 over a square root of n is square root of n is kind of the variance of the number of the difference between the number of the standard deviation of the number of heads, differences between heads and tails if we flip coins n times. So it's kind of like the square root of n is kind of like, the kind of expected difference that we're going to be getting when flipping n coins. Okay? And this is saying basically that what's the likelihood that if we see a difference where the difference is too many times more than the square root of n, okay? Well, alpha here is the significance. What is the likelihood, okay, that we that this big a difference? How confident are we? Are we confident that this occurred with less than a 1 in 100 chance? That's what alpha here is, the 1 over 100. Okay? And based on what is the confidence we want, okay, we can then look up C of alpha in a table, okay, and it will tell us basically if the gap between the two things is big enough, okay, that it is too much more than 1 over the square root of n, then the constant times the square root of n, then the distributions differ, and otherwise they're the same. Any questions about that? Okay, I happen to really like the KS test for a couple of reasons. One is I get a picture from it, okay? When I get a picture like this, I can look at this to myself and say, do I think these distributions are the same? Okay? And it gives me more confidence I'm doing something right or wrong than just whether I get a number out of it. Second, it's checking the entire distribution. Okay? And, it's looking not just at the mean and the standard deviation, but it's looking at the entire distribution. It's not just whether the means are the same. It's a question of whether or not, these really are the same distributions. Okay? Any questions about that? The other thing that's great about the KS test is that you can use it for many, many different things. Remember, I told you that sometimes you might want to know, is the height among men, okay, normally distributed? I take a sample, I have a 100, I have a sample of 300 men, and I know what their heights are. Is that height normally distributed? How would I tell? Okay, Well, suppose I sample. I know the mean of the distribution and the what you call the variance of your standard deviation of your distribution. Suppose I sample 300 points from a theoretical normal distribution, okay, with the height of that you observed and the standard deviation you observed in your 300 men. If your distribution was normally distributed, then the KS test shouldn't be able to tell the difference between it and between the men distribution and the theoretical samples from the normal. Okay, and here's an example of kind of what happens. This was, I believe, okay, where I took two samples of a particular normal distribution, and I plotted their cumulative distribution. And lo and behold, the biggest gap isn't that big, okay? When I did the same thing where one of the samples was normal and one of the samples was uniform, there was a place where there was a big gap, okay? And this big gap was too big, the KS test could tell that this shouldn't have happened, okay? Whereas this is in the bound of what would be expected. Any questions about that? Any questions about what the KS test is, why it's a good thing, how you would use it to tell whether two distributions are the same? Any questions? Okay, then look at this, think about it, and next class I'm going to show you another way of doing significance testing that I find is actually useful in a lot of experiments, talking about permutation tests, but we'll talk about that next time. Any other questions?
I did have a question about
Yes.
the KS test. Sorry, my mic wasn't working. What is the expected difference, like the expected deviation between two distributions that you would consider normal or enough to be matching?
Well, okay, what you would expect is, it's the way that I would be looking at it. I think that what my answer would be is I would go back to this, and it tells me that the biggest difference should be proportional to something that's the square root of n. It's a function of the square root of n. That's kind of what this thing is basically telling me, right? If the biggest difference, the gap here, is large relative to the square root of the number of samples. Notice everything is normalized, so it goes between 0 and 1. Square root of n is the number of steps on this plot. If I see a point where one of these plots gets too many times more than square root n, okay, ahead of the other plot, that is the sign of trouble. That is the sign of there being a difference, okay? And exactly how many times more than square root n, that's the kind of thing that you look up in a table, okay? That's what governs by this constant. Does that answer your question?
Yes, it does. Thank you.
Okay, very good. Anything else?
Why not use why look at the maximum difference? Why not look at the average difference or the median difference?
Well, why not look at the maximum or the average difference? Okay, well, first of all, if we looked at the average difference, okay, and it was a sign thing, the average difference would be 0, okay, because you're going to have as much mass of one above the other than as below the other. I think that's right, and maybe I'm being too glib. So what was your alternatives here? You were saying, why don't we look at the average difference?
Or
Well,
the average squared difference, or the median squared
Okay,
difference.
bottom line is, in order to show whether it's meaningful, you've got to have a derivation for what that constant there is, okay? And the claim is that Kolmogorov and Smirnov, when they worked that through the math, they were able to figure out what the expectation of the biggest gap was. Okay, it's not clear to me, again, the math for trying to figure out what the average difference might be. That's a different thing. It does seem to me you could probably base a test on that. But if so, you've got to come up with a measure of how big an average difference is unlikely to occur by chance, okay? If you come up with a measurement for that, then you've got a perfectly fair test. But that's why I guess KS looks at the maximum difference.
I mean, surely it would have been possible to derive that. I'm just like wondering, because like somebody's probably done that, because like we've
There
had.
may very well be another test that does that. Okay.
But why is this one so popular and the other one nobody's heard of?
Well, first of all, this one's popular because it works well. Okay, and you know, and the math here is rigorous and it works well. You could very well be talking about average absolute difference, but I don't. Again, I am. It seems like you could base a test on this. Okay, I don't have a argument as to why it would be better or wouldn't be better. Okay, but if you want to do your course project and figure that out, that's a great course project. Okay. Okay, it seems to me like, again, there should be the case that if the distributions, I'm agreeing with your premise that if the distributions are the same, the average absolute difference should be small, okay, or should be something bounded, okay? Now, what do you, what you call it? Now can you prove what the right threshold is, okay? And that's where I think the challenge is.
Okay.
Okay, any other questions? Okay, think about it and we will talk more about this next class. Okay, thanks a lot.